Hello everyone, I'm Professor Harrison, and welcome back to our module on statistical inference. Today we're going to be covering confidence intervals, what they are, why a single point estimate doesn't tell the whole story, and how to construct one from data. We're following Bess, an investigative journalist, on a cold case she can't let go, as she investigates financial cases where the numbers investors receive aren't giving them the full picture. A startup investment platform has been advertising 14% average annual returns to retail investors. 3 years of trading history with no range, no margin of error, just a single number. Bess's question is straightforward. What does that number actually tell you about what to expect going forward? She pulls up her case file. In the last video, we established what a sampling distribution looks like and introduced the standard error as a measure of how much the sample mean varies across samples. Today we use that directly. The fundamental problem with a point estimate is exactly what the sampling distribution shows you. A different sample would have given a completely different number. The sample mean is your best single guess at what the true expected return is going to be, but unfortunately it's only a guess. Reporting it without any indication of how precise or imprecise that guess is, well, that ends up being misleading, even if it is technically correct. A confidence interval solves that. Instead of a single number, a confidence interval gives you a range of plausible values for the true parameter. The formal definition is this. A confidence interval for a parameter at confidence level 1 minus alpha is an interval with a lower bound L and an upper bound U computed from the sample data. The defining property is this. Before you collect the data, the probability that the interval contains the true parameter equals 1 minus alpha. The most common levels used in practice are 90%, 95%, and 99%. For most finance work, 95% ends up being the default. Now let me be precise about what 95% confidence is actually saying, because this is one of the most frequently misread ideas in statistics. We are going to spend an entire video on it later, but for now here's the key idea to hold on to. If you ran the sampling and estimation procedure many times, each drawing a fresh sample, computing the sample mean, and building an interval, about 95% of those intervals would end up containing the true expected return. Not every interval is going to capture it, but 95% of them do. The confidence level is basically a statement about the long-run success rate of the procedure. We will come back to why that distinction matters, but for now, the practical takeaway is this. The interval gives you a plausible range for the true parameter, and the confidence level tells you how reliable the procedure is that produced it. Now let's talk about how to build one. Before we get to the formula, it helps to understand what the construction is actually doing. The sample mean is at the center of the interval. The critical value times the standard error is the margin of error. That is how far you stretch in each direction from the center to capture a plausible range. The margin of error is calibrated to the variability of the sampling distribution. You are essentially asking, given how much the sample mean tends to vary across samples, how wide does my range need to be to capture the true parameter 95% of the time? The general form of a confidence interval for a population mean is the sample mean plus or minus a critical value multiplied by the standard error of the mean. The standard error, as we found out in the last video, is sigma divided by the square root of n, where sigma is the standard deviation of returns and n is your sample size. From the last video, we know larger samples give smaller standard errors. The sample mean stabilizes as you collect more data. The critical value depends on the confidence level. For 95% confidence, it's approximately 1.96. For 90%, it's approximately 1.645. And for 99%, it's about 2.576. In the next video, we'll get into exactly where these values come from and which distribution to pull them from. But for now, 1.96 is going to be your starting point for 95% confidence. So let's build Bess's interval. The platform shows 36 months of returns. The sample mean monthly return is 1.2% per month. That annualizes to roughly the 14.4% which they were advertising. The monthly standard deviation is 6%. The standard error of the mean is going to be the 6% divided by the square root of the number of observations, which is 36. The square root of 36 is 6, so the standard error ends up being exactly 1% per month. So to get our 95% confidence interval, we do this. We take 1.2%, and then we add plus or minus 1.96 times the 1% standard error per month. That's 1.2% plus or minus about 2%, so the interval runs from roughly negative 0.8% to positive 3.2% per month. The lower bound here is negative. The interval includes 0. Based on 3 years of monthly data, you cannot conclude statistically that this platform has a positive expected monthly return. Now, some students find this surprising. They look at 36 months of positive returns, see a sample mean of 1.2% per month, and wonder how the interval can possibly include 0. The reason is the standard error. 1% per month is a large standard error relative to the sample mean. You would need the sample mean to be much larger or the standard error to be much smaller before the lower bound clears 0 reliably. The interval is not saying the platform is bad, it is just saying that the data isn't sufficient to establish that it is reliably good. So that is the core finding. The platform advertised 14% annual returns. The 95% confidence interval for the true mean monthly return is wide enough, though, that the true mean could possibly be negative. The sample mean is real. It is what the data actually show, but presenting it without the interval can be misleading because investors might think it's a reliable forecast when in reality they could potentially end up losing money on their investment. You end up with a number that looks definitive, but in truth it's anything but. Now, the width of that interval is determined by 3 things, and it's worth being explicit about each one. The first is the confidence level. Higher confidence means you have a wider interval. Switching from 95% to 99% means the critical value goes from 1.96 to 2.576. The margin of error widens from about 2% up to 2.6% per month. You capture the true parameter more often, but the range you're claiming becomes less precise. The second is the variability of the data. Monthly returns are noisy. The 6% standard deviation in this example would be typical for an equity investment. More volatile data means a larger standard error, which means a wider interval. There's nothing you can do about that except for get more data. The third thing driving the width of the interval is the sample size. More data will narrow the interval. A quick intuition is that every time you quadruple the sample size, the standard error gets cut in half. For example, if this platform had 144 months of history instead of 36, 12 years instead of 3, the standard error would drop from 1% down to around 0.5%. The margin of error would end up falling from 2% down to 1%. That's a meaningful improvement. 3 years is simply not enough data to make precise claims about the expected returns of an equity product. To put some concrete numbers on this, a fund with 10 years of monthly data and the same volatility would have a standard error of roughly 0.55% and a margin of error of around 1.1%. The interval would be roughly 1.2 plus or minus 1.1%. That still spans more than 2 percentage points, but at least the lower bound is above 0. In her article, Bess explains this to her readers. A 14% return is the mean of 36 monthly observations. It's not a forecast. The 95% confidence interval for the true expected monthly return includes 0. A platform that reports only the center and omits the range is being misleading because it's only reporting half the information. In fact, it's only reporting the half that looks better. So that is what a confidence interval is. It is a range of possible values for a population parameter built from sample data. It's designed so that the procedure that generated it captures the true value of the specified parameter a specified percentage of the time. The general form is the sample mean plus or minus a critical value times the standard error. Width is controlled by the confidence level, variability in the data, and the sample size. In the next video, we go deeper into where the critical values come from, because the right answer depends on something important about what you know and don't know about the variance.